Deep in a laboratory at MIT, physicists performed an experiment so precise it would have made Einstein and Bohr themselves weep with wonder. Using individual atoms cooled to temperatures colder than the vacuum of space, they stripped the most famous experiment in physics down to its quantum essence. What they discovered challenges everything we think we know about the nature of reality itself. The results were undeniable. Light exists as both a wave and a particle. But here's the mind-bending part. It cannot be observed in both forms at the same time. The very act of looking changes what exists. Think about that for a moment. The fundamental building blocks of our universe literally transform based on whether we're watching them or not. This isn't science fiction. This is quantum mechanics, and it's happening all around you right now. Every photon of light hitting your screen, every electron flowing through your device, every atom in your body is participating in this cosmic dance between existence and observation. Today, we're diving into one of the most profound mysteries in all of science: wave-particle duality, and the observer effect that suggests reality itself might depend on consciousness. Before we journey into this quantum rabbit hole, hit that like button and subscribe, because what we're about to explore will fundamentally change how you see the universe. We're going to examine experiments that defy common sense, theories that challenge the very foundations of reality, and discoveries that reveal our universe operates in ways so strange that even the greatest minds in physics spent decades arguing about what it all means. Prepare yourself. We begin. Picture the most important experiment in the history of physics. It's deceptively simple. Take a barrier with two slits cut into it. Shine light through those slits onto a screen behind them. What happens next reveals the deepest secrets about the nature of reality itself. When both slits are open, something extraordinary occurs. Instead of seeing two bright lines on the screen where light passed through each slit, you see an interference pattern. Bright and dark bands spread across the screen like ripples on a pond. This is the signature of waves interfering with each other. Light waves passing through one slit interfere with light waves passing through the other slit, creating regions where they amplify each other and regions where they cancel each other out. This makes perfect sense if light is a wave. Waves naturally create interference patterns. Drop two stones in a still pond and watch the ripples overlap, creating the same kind of pattern. For over a century, this experiment seemed to prove definitively that light consists of waves spreading through space. But then, scientists tried something that changed everything. They turned down the intensity of the light until only one photon at a time passed through the apparatus. Logic tells us that a single particle of light should go through either one slit or the other, creating two distinct lines on the screen. After all, how can one particle go through both slits simultaneously? Yet the interference pattern remained. Even when photons were fired one at a time, separated by hours, each individual particle somehow interfered with itself to create the same wave-like pattern. It's as if each photon travels through both slits simultaneously, acting like a wave that fills both paths at once, only to arrive at the detector as a single localized particle. This is where reality starts to break down. How can something be both a wave spread out through space and a particle localized at a specific point? How can a single photon go through two separate slits at the same time? The answer reveals one of the most unsettling truths about our universe. The mystery deepens when we try to peek behind the curtain. Scientists placed detectors at the slits to determine which path each photon actually takes. The moment they did this, something impossible happened. The interference pattern vanished completely. The photons began behaving like classical particles, each going through one slit or the other, creating exactly the two bright lines that common sense predicts. The act of measurement fundamentally changed the nature of reality. When no one was watching, photons behaved like waves, somehow traveling through both slits simultaneously. The moment scientists tried to observe which path the photons took, they collapsed into particles, forced to choose a single path through space. This is the observer effect in its most dramatic form. The very act of observation doesn't just reveal pre-existing properties of quantum objects. It actually determines what those properties will be. Before measurement, photons exist in what physicists call a superposition, simultaneously taking all possible paths through the experiment. The act of observation collapses this superposition, forcing quantum reality to choose one specific outcome from all the possibilities. Think about the implications. This suggests that unobserved quantum objects don't have definite properties. They exist in a fuzzy cloud of possibilities until the moment someone looks. It's as if the universe remains undecided about its own nature until consciousness forces it to make a choice. But here's where it gets even stranger. Recent experiments have pushed this mystery to its absolute limits. Scientists at MIT performed what they call the idealized version of the double-slit experiment, using individual atoms held at ultra-cold temperatures as both the particles being tested and the slits they pass through. By adjusting what they poetically call the atom's fuzziness, they could control exactly how wave-like or particle-like the system appeared. Their results confirmed something that Einstein and Bohr debated for decades but never thought could be tested with such precision. It is fundamentally impossible to observe both the wave and particle nature of light simultaneously. The more clearly you can determine which slit a photon went through, the more the interference pattern disappears. The more pronounced the interference pattern becomes, the less information you can gain about the photon's path. This isn't a limitation of our measuring instruments. It's not that we need better technology to see both aspects at once. The mathematics of quantum mechanics proves this complementarity is built into the fabric of reality itself. Wave and particle properties are mutually exclusive ways of describing the same quantum object, and nature allows us to choose which description we want to reveal through our experimental setup. The philosophical implications are staggering. If the fundamental building blocks of matter and energy don't have definite properties until observed, what does this say about the nature of reality itself? Does the universe exist in a definite state when no one is looking, or does observation actually participate in creating the reality we measure? Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in collapsing quantum possibilities into definite realities. In this view, the universe exists in a superposition of all possible states until a conscious observer makes a measurement, at which point reality crystallizes into the specific outcome that gets observed. Other interpretations avoid giving consciousness such a central role. They propose that any interaction with the environment, even with non-conscious measuring devices, can cause quantum systems to lose their wave-like properties and behave classically. In this view, it's not consciousness per se that collapses the wave function, but rather the unavoidable entanglement that occurs when quantum systems interact with the larger classical world. But even these more conservative interpretations can't escape the fundamental weirdness. Whether it's consciousness or environmental interaction that causes collapse, the basic mystery remains. Quantum objects somehow exist in multiple states simultaneously until something forces them to choose a definite configuration. The act of measurement, observation, or interaction fundamentally alters the nature of what exists. This isn't just abstract philosophy. The observer effect has been demonstrated countless times with increasingly sophisticated experiments. Scientists have shown that even the mere possibility of determining which path a particle takes is enough to destroy interference patterns. They've created experiments where the choice of whether to measure wave or particle properties can be made after the photon has already passed through the apparatus, suggesting that quantum events may not follow our intuitive notions of cause and effect. The precision of modern experiments has reached almost unimaginable levels. Researchers can now measure the relative waveness and particleness of quantum objects with mathematical exactitude. They've discovered that these two aspects of reality are perfectly complementary. When you include all the quantum mechanical factors, the sum of an object's wave-like and particle-like behaviors equals exactly 1. If something is perfectly wave-like, it shows 0 particle-like properties, and vice versa. Reality maintains a perfect balance, allowing quantum objects to be completely wave-like, completely particle-like, or any mixture in between, but never exceeding the total of one unit of existence. This mathematical relationship reveals something profound about the structure of reality. The universe seems to operate according to precise conservation laws that govern not just energy and momentum, but the very nature of existence itself. Wave-particle duality isn't a flaw in our understanding or a limitation of our instruments. It's a fundamental feature of how reality is constructed at its deepest level. The experimental evidence has grown so overwhelming that even the most skeptical physicists have been forced to accept that quantum mechanics describes something real and fundamental about our universe. The double-slit experiment and its countless variations have been performed with photons, electrons, atoms, and even large molecules. In every case, the same pattern emerges. Quantum objects behave as waves when unobserved and as particles when measured, with the act of observation playing a crucial role in determining what aspects of reality manifest. Yet, despite a century of experimental confirmation, the deeper meaning of these discoveries remains hotly debated. What exactly constitutes an observation? Does it require consciousness, or is any physical interaction sufficient? How does the transition occur between quantum superposition and classical definiteness? Why does the universe seem to exist in multiple states simultaneously until forced to choose? These questions push us to the very boundaries of human understanding. We're not just asking about the properties of matter and energy. We're asking about the fundamental nature of existence itself, the relationship between mind and matter, and the role of consciousness in shaping the reality we experience. The answers may force us to abandon our most basic assumptions about what it means for something to be real. The story of wave-particle duality began over 3 centuries ago with a debate between two brilliant minds about the nature of light itself. Isaac Newton, the towering genius who gave us the laws of motion and universal gravitation, proposed that light consists of tiny particles streaming through space. His contemporary Christian Huygens argued instead that light behaves like waves propagating through a mysterious medium called the luminiferous ether. For centuries, this debate raged back and forth as scientists performed increasingly sophisticated experiments to determine light's true nature. In the early 1800s, Thomas Young's double-slit experiment seemed to settle the matter decisively in favour of waves. The interference patterns Young observed could only be explained if light consisted of waves that could reinforce or cancel each other out. By the late 1800s, James Clerk Maxwell's electromagnetic theory provided a mathematical framework that explained light as oscillating electric and magnetic fields propagating through space at a fixed speed. The wave theory of light appeared triumphant. Every phenomenon from reflection and refraction to interference and diffraction could be elegantly explained using wave mechanics. Scientists believed they had finally solved one of nature's fundamental mysteries. Then came the photoelectric effect, and everything changed. In 1905, Albert Einstein made a startling proposal that would earn him the Nobel Prize and revolutionize our understanding of light. He suggested that light, despite all the evidence for its wave nature, also behaves as discrete particles called photons when it interacts with matter. The photoelectric effect occurs when light strikes a metal surface and knocks electrons loose. Classical wave theory predicted that the energy of the ejected electrons should depend on the brightness of the light. Brighter light should produce more energetic electrons. But experiments showed something completely different. The energy of the ejected electrons depended only on the color or frequency of the light, not its brightness. Blue light always produced more energetic electrons than red light, regardless of intensity. Einstein explained this paradox by proposing that light energy comes in discrete packets, or quanta, proportional to the light's frequency. Each photon carries a specific amount of energy determined by Planck's constant multiplied by the frequency. When a photon strikes an electron, it transfers all its energy in a single quantum transaction. This particle-like behavior explained the photoelectric effect perfectly, but seemed to contradict everything scientists knew about light's wave properties. The scientific community faced an impossible situation. Light clearly behaved like a wave in interference experiments, but acted like particles in photoelectric interactions. How could something be both a wave and a particle? The question seemed to violate the basic logical principle that something cannot simultaneously possess contradictory properties. Louis de Broglie provided the next crucial insight in 1924 when he proposed that wave-particle duality might not be limited to light. If photons could behave as both waves and particles, perhaps all matter might exhibit this dual nature. He suggested that electrons, protons, and even entire atoms might have wave-like properties under the right conditions. De Broglie's hypothesis seemed outrageous. How could solid matter behave like waves? Yet, within a few years, experiments confirmed that electrons could indeed create interference patterns just like light waves. Clinton Davison and Lester Germer scattered electrons off crystal surfaces and observed the same kind of wave interference that Young had seen with light over a century earlier. The implications were staggering. Not only was light both wave and particle, but matter itself shared this mysterious dual nature. The classical distinction between waves and particles, between energy and matter, began to blur into something far more subtle and strange. Niels Bohr attempted to make sense of these discoveries through his principle of complementarity. He argued that wave and particle descriptions are not contradictory, but complementary aspects of a deeper quantum reality. The experimental setup determines which aspect of this duality becomes manifest. Experiments designed to reveal wave properties will show waves. Experiments designed to detect particles will find particles. But no single experiment can reveal both aspects simultaneously. This complementarity principle resolved the logical paradox by recognizing that wave and particle are simply different ways of describing the same quantum object under different experimental conditions. The quantum world doesn't consist of classical waves or classical particles, but of something more fundamental that can manifest as either depending on how we choose to interact with it. Yet Bohr's interpretation raised new philosophical questions that continue to puzzle physicists today. If quantum objects only exhibit definite properties when measured, what exists between measurements? Do electrons have definite positions and momenta when no one is looking, or do these properties only come into existence through the act of observation? Einstein never accepted Bohr's interpretation, famously declaring that God does not play dice with the universe. He believed that quantum mechanics, despite its experimental success, must be incomplete. There had to be hidden variables, unknown properties that would restore determinism and objective reality to physics if only we could discover them. Einstein spent the last decades of his life searching for a more complete theory that would eliminate the apparent randomness and observer dependence of quantum mechanics. The debate between Einstein and Bohr became one of the most famous intellectual disputes in the history of science. Both men were brilliant, both were convinced they were right, and both were grappling with experimental results that seemed to defy rational explanation. Their disagreement wasn't just about physics, but about the fundamental nature of reality itself. The arguments between these two giants of physics reached their climax in a series of thought experiments designed to expose the absurdities each believed lay at the heart of the other's interpretation. Einstein proposed scenarios where quantum mechanics seemed to predict impossible instantaneous connections between distant particles. Bohr countered with detailed analyses showing how quantum complementarity could account for every experimental result without logical contradiction. But neither man could have imagined the experiments that would eventually settle their debate. In 2022, nearly a century after their famous discussions, the MIT team led by Wolfgang Ketteler performed what can only be described as the most elegant test of quantum reality ever devised, using atoms cooled to temperatures so low that thermal motion virtually stops. They created conditions where individual quantum particles could be manipulated with unprecedented precision. The setup was breathtaking in its simplicity. Instead of slits cut into barriers, the researchers used individual atoms arranged in optical lattices as the pathways for light to travel. By adjusting magnetic fields and laser intensities, they could control exactly how fuzzy or well-defined each atom's position became. This fuzziness, measured by quantum uncertainty, directly controls whether the system exhibits wave-like or particle-like behavior. When the atoms were made very fuzzy, with highly uncertain positions, the light passing through them created perfect interference patterns characteristic of waves. When the atoms were pinned down to precise locations, eliminating their fuzziness, the wave interference disappeared completely, and light behaved as discrete particles following definite paths. The beauty of this experiment lies in its ability to continuously tune between these extremes. By gradually adjusting the atom's fuzziness, the researchers could watch wave-particle duality transform smoothly from one extreme to the other. It's like having a quantum dimmer switch that controls the very nature of reality itself. The mathematical precision of these results finally resolved the Einstein-Bohr debate with definitive clarity. The data showed perfect complementarity between wave and particle properties, exactly as Bohr had predicted. When coherence and quantum uncertainty were properly accounted for, the sum of waveness and particleness equaled exactly 1, never more, never less. Nature maintains perfect bookkeeping in its quantum accounts. Einstein's hope for hidden variables that would restore classical determinism was definitively ruled out. The randomness and observer dependence of quantum mechanics aren't flaws to be corrected, but fundamental features of how reality operates at its deepest level. The universe really does seem to exist in multiple states simultaneously until observation forces it to choose. Yet the resolution of this historic debate has opened even stranger questions about the nature of observation itself. What exactly constitutes a measurement that can collapse quantum superpositions into definite states? Does it require conscious awareness, or is any physical interaction sufficient to trigger the transition from quantum to classical behavior? Modern physics has revealed that the answer is more subtle than either pure consciousness or simple physical interaction. The key concept is called quantum decoherence, and it explains how quantum systems lose their wave-like properties through entanglement with their environment. When a quantum particle interacts with air molecules, photons, electromagnetic fields, or measuring instruments, it becomes entangled with an enormous number of environmental degrees of freedom. This entanglement doesn't require consciousness or even sophisticated measuring devices. A single photon bouncing off an electron is enough to entangle that electron with the electromagnetic field, causing its quantum superposition to decay into classical behavior. The larger and more complex a quantum system becomes, the more rapidly it decoheres, which explains why we don't observe quantum effects like superposition and interference in our everyday macroscopic world. Decoherence theory has been experimentally verified in countless studies, showing how quantum systems transition to classical behavior as they interact with their surroundings. The process happens incredibly quickly for large objects. A dust particle floating in air loses its quantum coherence in less than a billionth of a second. A bacterium would decohere almost instantaneously. This explains why quantum effects remain hidden at the scales of ordinary experience while manifesting clearly in carefully isolated microscopic systems. But decoherence doesn't completely eliminate the mystery of quantum measurement. It explains how quantum systems appear to become classical through environmental interaction, but it doesn't explain why only one specific outcome is observed from all the possibilities present in the quantum superposition. The measurement problem, as physicists call it, remains one of the deepest unsolved puzzles in quantum mechanics. Some interpretations suggest that all possible measurement outcomes actually occur, but in parallel universes that branch off from each quantum interaction. In this many worlds view, every time a quantum measurement happens, the universe splits into multiple copies, with each possible result realized in a different branch. We only experience one branch, but all possibilities remain equally real in the multiverse as a whole. Other interpretations propose that quantum probabilities represent genuine randomness built into the fabric of reality itself. When a quantum system is measured, nature truly makes a random choice from the available options, with probabilities determined by the quantum wave function. This interpretation preserves the single universe view but accepts fundamental indeterminism as a feature of reality. Still, other approaches suggest that our entire framework for thinking about quantum measurement may be flawed. Perhaps the wave function never actually collapses, and what we interpret as measurement is simply our classical approximation of a purely quantum process. In this view, the classical world emerges from quantum foundations through information-theoretic relationships that don't require any special measurement postulates. The philosophical implications of these different interpretations stretch far beyond physics into questions about the nature of existence, consciousness, and reality itself. If the many worlds interpretation is correct, then countless copies of you exist across parallel universes, experiencing all possible variations of quantum outcomes. If objective collapse theories are right, then consciousness might play a fundamental role in shaping reality through observation. If purely quantum approaches are valid, then our classical concepts of definite properties and objective reality may be approximations that break down at the deepest levels of analysis. These aren't merely academic debates. The interpretation of quantum mechanics affects how we understand our place in the universe and the relationship between mind and matter. It determines whether we live in a deterministic cosmos where everything is predetermined, a probabilistic universe where chance plays a fundamental role, or a multiverse where all possibilities coexist in parallel realities. The experimental evidence continues to accumulate, pushing these interpretations to ever more stringent tests. Delayed choice experiments have shown that the decision to measure wave or particle properties can be made after a photon has already completed its journey through an experimental apparatus, yet this future choice retroactively determines which aspect of reality manifests. These results suggest that quantum events may not follow our intuitive notions of temporal causality. Quantum eraser experiments demonstrate even more bizarre possibilities. Scientists can first perform measurements that destroy interference patterns, then later perform additional measurements that restore the interference, effectively erasing the information about which path particles took. The interference patterns reappear as if the original measurements never happened, suggesting that quantum information can be manipulated in ways that seem to violate our understanding of cause and effect. Entanglement experiments reveal non-local correlations between quantum particles that remain mysteriously connected even when separated by vast distances. When the wave or particle properties of one entangled photon are measured, its distant partner instantly exhibits complementary properties regardless of the space between them. These quantum correlations appear to operate faster than light, challenging our concepts of locality and the independence of distant objects. Each new experiment reveals additional layers of strangeness in quantum mechanics while confirming the theory's mathematical predictions with ever greater precision. The quantum world operates according to principles so foreign to everyday experience that even physicists who work with these phenomena daily admit they don't truly understand what it all means for the nature of reality. Yet this fundamental mystery hasn't prevented quantum mechanics from becoming the most practically successful theory in the history of science. Every electronic device, every laser, every computer chip, every LED light depends on quantum mechanical principles for its operation. The technologies that define modern civilization emerged from our understanding of wave-particle duality and quantum behavior. Quantum computers exploit the wave-like superposition properties of quantum bits to perform parallel calculations on multiple possible solutions simultaneously. Quantum cryptography uses the particle-like measurement properties to create unbreakable communication protocols. Quantum sensors harness interference effects to achieve measurement precision that surpasses all classical limits. These applications demonstrate that wave-particle duality isn't merely an abstract curiosity, but a practical resource that can be harnessed for technological advancement. The same quantum principles that puzzle philosophers enable revolutionary capabilities in computation, communication, and measurement that would be impossible in a purely classical world. The story of wave-particle duality continues to unfold as scientists push the boundaries of what can be observed and measured. Recent experiments have demonstrated quantum behavior in increasingly large and complex systems, from individual molecules to microscopic mechanical oscillators to clouds of ultra-cold atoms. Each advance reveals new aspects of the quantum classical boundary and new questions about when and why classical behavior emerges from quantum foundations. Some researchers are exploring whether quantum effects might persist even in biological systems, potentially playing roles in photosynthesis, bird navigation, and even consciousness itself. Others investigate quantum behavior in exotic states of matter, where particles exhibit properties that don't fit neatly into either wave or particle categories. Still others probe the deepest foundations of quantum theory, searching for more fundamental principles that might explain why reality operates according to quantum rules. The questions raised by wave-particle duality reach into every corner of physics, from the smallest subatomic scales to the largest cosmic structures. Does quantum mechanics apply to black holes and the expansion of the universe? Do quantum effects influence the arrow of time and the apparent flow of causality? Could consciousness itself be a quantum phenomenon that bridges the gap between subjective experience and objective reality? These investigations continue because wave-particle duality represents more than just an interesting property of light and matter. It reveals something profound about the relationship between observation and reality, between what exists and what can be known, between the physical world and the conscious minds that study it. The deeper we probe into quantum mechanics, the more we discover that reality itself may be far stranger and more wonderful than we ever imagined. The deeper implications of quantum mechanics stretch far beyond laboratory experiments into the very fabric of how information and reality interconnect. At the quantum level, information isn't just something we collect about particles, it appears to be what particles fundamentally are. This revelation transforms our understanding of existence from solid matter occupying space to patterns of information that can manifest in different forms depending on how they are accessed. Consider what happens when quantum information is measured. The act of gaining knowledge about a quantum system doesn't just reveal pre-existing properties. It appears to create those properties in the first place. Before measurement, a photon doesn't have a definite position or momentum. These aren't hidden variables waiting to be discovered. The quantum state contains only probabilities, only potential realities that exist in mathematical superposition until the moment someone extracts information from the system. This relationship between information and reality becomes even more profound when we examine quantum entanglement. When two particles become entangled, they form a single quantum system, regardless of the distance separating them. Measuring the wave properties of one particle instantly determines the particle properties of its distant partner. The information about their combined state isn't stored locally in either particle, but exists as a non-local connection that transcends our ordinary concepts of space and time. Einstein famously called this spooky action at a distance, and refused to accept that nature could operate through such mysterious correlations. He believed there had to be hidden variables, local properties that would explain these connections without requiring instantaneous communication between distant particles. Yet decades of increasingly sophisticated experiments have confirmed that quantum entanglement is real and that no local hidden variables can account for the correlations observed in nature. The implications are staggering. If information about quantum systems can exist in non-local forms, then our concept of reality as consisting of separate objects with independent properties begins to break down. The universe starts to look less like a collection of distinct things and more like a vast network of information relationships that transcend the boundaries we normally perceive between separate entities. This informational view of quantum mechanics suggests that wave-particle duality might be just one example of a deeper principle governing how reality manifests from underlying information patterns. What we call waves and particles could be different ways that quantum information presents itself to classical measuring devices, like different views of the same multidimensional object projected onto two-dimensional screens. Modern quantum field theory supports this perspective by describing particles as excitations of underlying quantum fields that fill all of space and time. In this framework, what we perceive as separate particles are localized patterns of field energy, like waves on an ocean, that temporarily take the form of discrete peaks before dissolving back into the continuous medium. The wave-particle duality emerges naturally because the same quantum field can manifest as wave-like phenomena when spread out, or particle-like phenomena when localized, depending on how the field is probed by measurements. But quantum field theory reveals even stranger possibilities. Virtual particles constantly pop into existence throughout empty space, borrowing energy from the quantum vacuum and paying it back so quickly that their existence can't be directly observed. These virtual particles aren't just mathematical artifacts, they produce measurable effects like the Casimir force, where empty space exerts pressure on closely spaced metal plates due to the quantum fluctuations of the electromagnetic field. The quantum vacuum itself becomes a seething sea of potential particles and antiparticles that briefly materialize before annihilating each other and disappearing. This suggests that even empty space has structure and energy, that nothingness itself possesses properties that can influence the behavior of real particles passing through it. The boundary between what exists and what doesn't becomes increasingly blurred at quantum scales. Some interpretations push this informational view to its logical extreme, suggesting that reality might be fundamentally computational in nature. If quantum states are information patterns and quantum evolution follows mathematical rules, then perhaps the universe operates like a vast quantum computer processing information about its own states. In this view, space and time themselves might emerge from more fundamental information processing relationships, like the virtual reality generated by a computer simulation. This computational perspective offers new ways to understand wave-particle duality and the observer effect. When we measure a quantum system, we're essentially extracting information from the universal quantum computation. The act of measurement forces the system to produce classical output from its quantum processing, collapsing superpositions into definite states that can interface with our classical measuring devices and conscious minds. The role of consciousness in quantum mechanics remains one of the most contentious and fascinating aspects of these discoveries. Some interpretations suggest that consciousness plays a fundamental role in collapsing quantum superpositions into definite realities. In this view, the universe exists in a superposition of all possible states until conscious observation forces it to choose specific outcomes from the quantum menu of possibilities. Other interpretations avoid giving consciousness such a central role, arguing that any physical interaction can cause quantum decoherence regardless of whether conscious observers are present. A photon scattered by an electron, a particle absorbed by a detector, or even a quantum system interacting with thermal radiation can cause wave functions to collapse into particle-like behavior. Consciousness might simply be one type of physical process among many that can extract information from quantum systems. Yet even these more conservative interpretations can't completely eliminate the mystery of consciousness and quantum mechanics. If conscious observers are physical systems that evolved within the quantum universe, how do classical brains built from quantum components manage to extract definite information from quantum superpositions? The transition from quantum possibilities to conscious experience remains unexplained by purely physical theories. Some researchers propose that consciousness itself might be a quantum phenomenon that operates according to principles we don't yet understand. Perhaps conscious awareness emerges from quantum coherence effects in biological systems, allowing minds to directly interface with quantum information in ways that classical computers cannot. This could explain how consciousness seems to have special access to definite experiences despite being built from fundamentally uncertain quantum components. The delayed choice experiments add another layer of mystery to these questions. In these experiments, scientists can decide whether to measure wave or particle properties after a photon has already completed its journey through the experimental apparatus. Remarkably, this future choice appears to retroactively determine which aspect of wave-particle duality manifests, as if the decision to measure waves or particles reaches backward in time to influence events that already occurred. These results challenge our most basic assumptions about causality and temporal ordering. If future measurements can influence past events, then the flow of time might not work the way we intuitively imagine. The quantum world seems to operate according to a different logic where effects can precede their causes and where future choices can influence past realities. Wheeler's delayed choice experiment pushes this concept even further, by suggesting that conscious observers might retroactively determine not just the properties of particles but the entire history of the universe. If quantum events remain undetermined until observed, and if astronomical observations can affect the quantum states of photons that have been traveling for billions of years, then our present measurements might be participating in creating the past reality of the cosmos itself. This possibility leads to what Wheeler called the participatory universe, a cosmos where conscious observers don't just discover pre-existing reality, but actively participate in creating the reality they observe through their choice of measurements. In this view, the universe doesn't have a definite history until conscious beings evolve to observe it, at which point the act of observation retroactively creates the chain of events that led to the emergence of consciousness in the first place. The mathematical formalism of quantum mechanics supports these strange possibilities through its treatment of time symmetry. The equations that govern quantum evolution work equally well forward and backward in time, suggesting that quantum processes might not distinguish between past and future in the way classical physics assumes. What we interpret as causes and effects might be different aspects of atemporal quantum relationships that transcend our ordinary experience of sequential time. Recent experiments in quantum eraser configurations have demonstrated these temporal puzzles with increasing sophistication. Scientists can perform measurements that destroy interference patterns, then later perform additional measurements that restore the interference, effectively erasing the information about which path particles took. The interference patterns reappear as if the original path-determining measurements never happened, despite the fact that the erasing measurements occur after the particles have already been detected. These quantum eraser experiments suggest that information itself might be more fundamental than the events that create it. The quantum information about which path a particle takes can be created and destroyed independently of the particle's actual journey through the apparatus. This informational perspective implies that reality might consist of information patterns that can be manipulated in ways that seem to violate our intuitive understanding of cause and effect. The growing field of quantum information theory is revealing that information processing might be the most fundamental activity in the universe. Every quantum interaction involves the exchange, creation, or destruction of information. Every measurement extracts information from quantum systems. Every quantum computation processes information according to quantum mechanical rules. The entire universe might be understood as a vast information processing system where matter and energy are simply different forms of organized information. This informational view offers new insights into wave-particle duality itself. Waves and particles might represent different ways of encoding and processing information about quantum systems, rather than different types of physical objects. When information is distributed across space and time, it manifests as wave-like phenomena. When information is localized at specific points, it appears as particle-like behavior. The observer effect occurs because different types of measurements extract different kinds of information from the same underlying quantum system. The practical applications of these discoveries continue to expand as scientists learn to manipulate quantum information with increasing precision. Quantum computers use superposition and entanglement to process information in ways that would be impossible with classical systems. Quantum cryptography exploits the no-cloning theorem to create communication protocols that are guaranteed to be secure by the laws of physics themselves. Quantum sensors harness interference effects to achieve measurement sensitivities that approach the fundamental limits imposed by quantum mechanics. These devices can detect gravitational waves, measure magnetic fields with unprecedented precision, and even probe the quantum properties of biological systems. The wave-particle duality that once seemed like a philosophical puzzle has become a practical resource for technologies that surpass all classical limitations. But perhaps the most profound application lies in our growing understanding of quantum foundations themselves. As we develop better tools for probing quantum systems and manipulating quantum information, we're uncovering deeper layers of the mystery that connects observation, information, and reality. Each new experiment reveals additional aspects of how consciousness, measurement, and quantum mechanics interact in ways that continue to challenge our most fundamental assumptions about existence itself. The story of wave-particle duality has evolved from a simple question about the nature of light into a comprehensive exploration of reality, information, and consciousness that touches every aspect of physics and philosophy. What began as an attempt to understand whether light consists of waves or particles has revealed that this question itself was based on classical assumptions that don't apply to the quantum world. Instead of waves or particles, we've discovered quantum objects that transcend these classical categories entirely. Instead of objective reality independent of observation, we've found a participatory universe where consciousness and measurement play fundamental roles in determining what exists. Instead of deterministic laws governing the behavior of definite objects, we've uncovered probabilistic relationships between information patterns that exist in superposition until extracted by observation. These discoveries continue to generate new questions faster than we can answer them. How does classical reality emerge from quantum foundations? What constitutes a measurement that can collapse superpositions? Does consciousness play a special role in quantum mechanics, or is it simply one physical process among many? How do quantum effects scale up from microscopic to macroscopic systems? What are the ultimate limits of quantum information processing? The answers to these questions will likely require new conceptual frameworks that go beyond our current understanding of physics, consciousness, and reality itself. We may need to develop new mathematics, new experimental techniques, and perhaps even new ways of thinking about existence that can accommodate the profound strangeness of quantum mechanics while maintaining logical consistency and experimental testability. What remains certain is that wave-particle duality has opened a window into aspects of reality that are far stranger and more wonderful than classical physics ever imagined. The universe revealed by quantum mechanics operates according to principles that challenge every assumption we might make about how existence works. Yet these same principles enable the complex structures and processes that make consciousness and life possible. The quantum world doesn't just exist alongside our classical experience. It underlies and enables everything we observe and think and feel. Every atom in our bodies, every photon entering our eyes, every electron flowing through our neurons participates in the cosmic dance between waves and particles, between possibility and actuality, between the observed and the observer that constitutes the deepest mystery of existence itself. The quantum revolution didn't stop with photons and electrons. As scientists pushed the boundaries of what could be tested, they discovered that wave-particle duality extends to objects far larger and more complex than anyone thought possible. In laboratories around the world, researchers have demonstrated quantum behavior in molecules containing hundreds of atoms, in microscopic mechanical oscillators, and even in biological systems where quantum effects might play crucial roles in the most fundamental processes of life itself. Consider the breathtaking experiments conducted with buckyballs, those soccer ball-shaped molecules made of 60 carbon atoms. When fired through double-slit apparatus, these massive molecular structures create the same ghostly interference patterns that single photons produce. Each buckyball somehow passes through both slits simultaneously, interfering with itself to create wave-like patterns on the detection screen. We're talking about objects containing 360 protons, 360 neutrons, and 360 electrons, all somehow existing in quantum superposition until the moment of measurement. The implications stretch far beyond laboratory curiosities. If molecules this large can exhibit wave-particle duality, where exactly does the quantum world end and the classical world begin? The boundary keeps moving as experiments become more sophisticated. Scientists have now demonstrated quantum effects in objects containing thousands of atoms, pushing us toward a regime where quantum mechanics might influence systems large enough to see with the naked eye. But the most astonishing discoveries may be happening inside living cells right now. Mounting evidence suggests that biological systems have evolved to exploit quantum mechanical effects in ways that would make quantum engineers weep with envy. Photosynthesis, the process that powers virtually all life on Earth, appears to use quantum superposition to achieve energy transfer efficiencies that approach theoretical perfection. In photosynthetic complexes, energy from absorbed photons must travel through networks of molecules to reach reaction centers where it gets converted to chemical energy. Classical physics predicts this energy would take random walks through the molecular maze, losing much of its power along the way. Yet plants and bacteria achieve energy transfer efficiencies of nearly 100%, far better than any artificial solar cell we've managed to create. The secret lies in quantum coherence. Recent experiments reveal that energy in photosynthetic systems exists in superposition states, simultaneously exploring all possible pathways through the molecular network. Like water finding the most efficient route down a mountainside, quantum energy finds the optimal path through biological machinery by trying all routes at once. Only when the energy reaches its destination does the quantum superposition collapse into a definite classical outcome. This biological quantum mechanics operates at temperatures and timescales that should destroy delicate quantum effects. Living cells are warm, wet, noisy environments where quantum coherence typically disappears in femtoseconds, yet evolution has apparently found ways to protect and exploit quantum phenomena even in these hostile conditions, suggesting that life itself might be fundamental staggering if quantum effects are quantum mechanical in nature. The implications for consciousness can persist in the chaotic environment of living cells. Perhaps they play roles in the neural processes that generate awareness and experience. Some researchers propose that consciousness emerges from quantum computations occurring in microtubules, the protein structures that form cellular scaffolding throughout the brain. Others suggest that quantum entanglement between neurons might enable the unified conscious experience that somehow emerges from billions of separate brain cells. These ideas remain highly speculative, but they point toward possibilities that could revolutionize our understanding of mind and matter. If consciousness involves quantum processes, then the observer effect might be more than just a measurement problem in physics. It could represent the fundamental mechanism through which awareness interfaces with reality, the process by which subjective experience emerges from objective physical processes. The technology emerging from quantum mechanics continues to push these questions in new directions. Quantum computers don't just process information differently from classical machines, they operate according to principles that challenge our basic concepts of computation and information storage. When a quantum computer performs calculations, it doesn't follow a single sequence of logical operations like classical computers do. Instead, it explores all possible computational pathways simultaneously through quantum superposition. A quantum bit, or qubit, can exist in superposition states that represent both 0 and 1 at the same time. Multiple qubits can become entangled, creating collective quantum states that encode exponentially more information than classical bits ever could. When quantum algorithms run on these systems, they perform vast numbers of parallel calculations before finally collapsing into classical outputs that provide answers to problems that would take classical computers longer than the age of the universe to solve. But here's where the measurement problem becomes a practical engineering challenge. Quantum computers must maintain delicate superposition states throughout their calculations while remaining isolated from environmental disturbances that would cause premature decoherence. The moment unwanted measurements occur, quantum advantages disappear as superpositions collapse into classical states. Engineers must create what amounts to artificial realities where quantum effects can persist long enough to be useful. The success of these efforts demonstrates that wave-particle duality and quantum superposition aren't just abstract concepts but practical resources that can be harnessed for technological applications. Quantum computers already exceed classical machines for certain specialized tasks, and their capabilities continue to expand as researchers develop better ways to control quantum systems. Quantum cryptography represents another domain where wave-particle duality becomes a practical tool. The fundamental principles that make quantum mechanics so mysterious also make it ideal for creating unbreakable communication systems. When quantum information is transmitted between parties, any attempt to intercept or eavesdrop on the communication necessarily disturbs the quantum states being transmitted. This disturbance can be detected by the legitimate communicators, immediately alerting them to the presence of unauthorized observers. The security of quantum cryptography doesn't depend on mathematical complexity or computational assumptions that might someday be broken by more powerful computers. Instead, it relies on the fundamental laws of quantum mechanics themselves. The no-cloning theorem proves that quantum information cannot be perfectly copied, while the uncertainty principle ensures that complete information about quantum states cannot be extracted without disturbing those states. These aren't limitations of current technology, but absolute physical laws that govern how information can be processed in our universe. Yet even these practical applications raise deep questions about the nature of information and reality. If quantum information cannot be cloned, what makes it different from classical information that can be copied indefinitely? If quantum states cannot be measured without disturbance, what exists before measurement occurs? These aren't just technical challenges, but fundamental mysteries about how information and existence relate to each other. The answers may require us to abandon traditional distinctions between information and physical reality. In quantum mechanics, information isn't just something we have about systems, it appears to be what systems fundamentally are. The wave function that describes a quantum system is pure information, mathematical relationships that encode possibilities rather than definite properties. When we measure quantum systems, we're not just discovering pre-existing information, but participating in the process by which information becomes reality. This informational view of quantum mechanics connects to broader questions about the nature of physical law and mathematical structure. Why does the universe operate according to mathematical principles? Why do abstract mathematical relationships like wave functions and probability amplitudes correspond so precisely to experimental results? Some physicists propose that mathematics isn't just a tool for describing reality, but the fundamental substance from which reality is constructed. In this view, particles aren't mathematical objects, they are mathematical objects. Wave functions aren't descriptions of physical systems, they are the physical systems. The universe becomes a vast mathematical computation where physical processes correspond to mathematical operations, and where consciousness emerges as certain types of mathematical structures become complex enough to model themselves and their environment. These ideas push us toward a particip and physical-atory universe where consciousness, information, reality are different aspects of a single underlying mathematical structure. The observer effect occurs because conscious minds are mathematical patterns that can interface with other mathematical patterns through measurement processes. Wave-particle duality emerges because the same mathematical structures can be accessed through different types of interface protocols that reveal different aspects of their underlying information content. But mathematics itself poses puzzles that go beyond physics. Why do mathematical structures exist at all? Why do some mathematical relationships correspond to physical reality, while others remain abstract possibilities? How do mathematical patterns become aware of themselves through the emergence of consciousness? These questions push us beyond science into domains where physics, mathematics, philosophy, and perhaps even theology begin to converge. The delayed choice experiments we discussed earlier take on new significance in this mathematical context. If mathematical structures exist independently of time, then past and future might be equally real aspects of a timeless mathematical reality. Conscious observers might not create the past through retroactive measurements, but rather access different aspects of mathematical structures that exist outside temporal sequence altogether. This timeless view of reality offers new perspectives on causality and free will. If all moments exist simultaneously in mathematical space, then what we experience as temporal sequence might emerge from the structure of consciousness rather than from the flow of physical time. Our choices and decisions might not create the future, but rather determine which aspects of an already existing mathematical reality we experience through our conscious observations. The quantum eraser experiments become even more mysterious from this perspective. When information about particle paths is created and then destroyed, we're not manipulating physical processes in time, but rather changing which aspects of mathematical reality become accessible to conscious observation. The interference patterns that disappear and reappear reflect changes in how mathematical structures interface with measuring systems rather than changes in physical events occurring in temporal sequence. These ideas remain highly speculative, but they illustrate how wave-particle duality opens doors to radical reconceptions of reality that go far beyond the simple question of whether light consists of waves or particles. We've moved from asking about the properties of photons to questioning the nature of existence itself, the relationship between mathematics and physics, and the role of consciousness in determining what aspects of reality become manifest through observation. The practical implications continue to expand as our understanding deepens. Quantum sensors exploit interference effects to achieve measurement precisions that approach fundamental physical limits. These devices can detect gravitational waves rippling through space-time, measure magnetic fields with sensitivity that exceeds classical possibilities by orders of magnitude, and probe biological systems with unprecedented resolution. The wave-like properties of quantum objects become tools for exploring reality at scales and sensitivities that would be impossible with purely classical instruments. Medical imaging systems based on quantum principles are beginning to reveal cellular and molecular processes in living organisms with clarity that was unimaginable just decades ago. Quantum-enhanced microscopy can observe biological structures without the damage typically caused by high-intensity illumination, while quantum sensors can detect magnetic fields generated by neural activity with precision that rivals the most sophisticated brain imaging technologies currently available. These applications demonstrate that wave-particle duality isn't just a curiosity for physics laboratories, but a fundamental feature of nature that can be harnessed for practical benefit. The same quantum principles that challenge our philosophical assumptions about reality also enable technologies that extend human capabilities in ways that seemed like science fiction just a generation ago. But perhaps the most profound applications lie in our growing ability to create and manipulate quantum systems with precision that rivals nature's own achievements. Scientists can now trap individual atoms in optical lattices, control their quantum states with laser pulses, and create artificial quantum materials with properties that don't exist anywhere in the natural world. We're moving beyond simply observing quantum effects to actively engineering quantum realities according to our designs and specifications. This technological mastery over quantum systems raises new questions about the boundary between natural and artificial reality. If we can create quantum systems that exhibit wave-particle duality according to our specifications, are we discovering universal principles or constructing particular realities? When we design quantum computers that process information through superposition and entanglement, are we building machines that operate according to pre-existing laws, or are we participating in the creation of new forms of reality that didn't exist before conscious minds learned to manipulate quantum systems? The answers may depend on deeper questions about whether mathematical structures exist independently of the physical universe, or whether mathematics and physics co-evolve through processes that include the emergence of consciousness and intelligence. If conscious observers play fundamental roles in collapsing quantum possibilities into definite realities, then the development of technologies that can control quantum systems might represent a new phase in the evolution of reality itself. We may be approaching a threshold where the boundary between discovering and creating reality becomes increasingly blurred. As our ability to manipulate quantum systems approaches the precision that nature achieves in biological systems, we're gaining the power to engineer realities that transcend the distinction between natural and artificial, between given and constructed, between discovered and invented. The implications stretch far beyond technology into questions about the ultimate nature and destiny of consciousness in a quantum universe. If consciousness plays fundamental roles in quantum measurement, and if we're developing technologies that can control quantum systems with unprecedented precision, then we may be approaching capabilities that could transform not just our understanding of reality, but reality itself. These possibilities remain largely speculative, but they illustrate how wave-particle duality opens pathways toward futures that would have been unimaginable without the quantum revolution. We've moved from simple questions about the nature of light to comprehensive explorations of consciousness, reality, and the role of intelligence in shaping the universe itself. The journey continues as each new experiment reveals additional layers of quantum strangeness while confirming the mathematical precision of quantum mechanical predictions. We're not just studying the universe, we're discovering our place within it as conscious observers who participate in the ongoing creation of reality through our choices about what to measure and how to measure it. The quantum universe doesn't just exist around us, it exists through us, as conscious beings capable of collapsing possibilities into actualities through the fundamental act of observation. Wave-particle duality reveals that we're not separate from the reality we study, but integral participants in the cosmic process by which potential becomes actual, by which mathematical possibilities become experienced realities, by which the universe becomes aware of itself through the emergence of consciousness capable of quantum observation and measurement. This profound relationship between observer and observed extends into realms that would have seemed like pure fantasy just decades ago. Modern quantum experiments have revealed that the act of measurement can influence events that haven't happened yet, creating causal loops that challenge everything we thought we knew about the arrow of time itself. In laboratories around the world, scientists are performing experiments where future decisions retroactively determine past realities. They set up quantum systems where particles travel through experimental apparatus, then make choices about how to measure them after the particles have already completed their journeys. Remarkably, these future measurement decisions appear to reach backward in time, determining whether particles exhibited wave-like or particle-like behavior during their earlier passage through the experiment. The implications are staggering. If future observations can influence past events, then causality itself becomes a quantum phenomenon subject to superposition and uncertainty. The linear progression from cause to effect that governs our everyday experience might be an approximation that breaks down when consciousness interfaces directly with quantum systems. Consider what this means for the nature of free will and determinism. Classical physics suggested that the future is determined by past events according to fixed laws. Quantum mechanics introduced randomness and probability, but still maintained temporal ordering where causes precede effects. Now we're confronting experimental evidence that conscious choices might influence events across temporal boundaries, creating feedback loops between past and future that transcend our normal understanding of sequential time. These temporal paradoxes become even stranger when we examine quantum entanglement across time. Scientists have demonstrated that particles can become entangled not just across space, but across time itself. A measurement performed on a particle today can become correlated with measurements that will be performed on other particles tomorrow, or that were performed yesterday. The quantum correlations that Einstein called spooky action at a distance now extend into spooky action across time. The mathematical formalism of quantum mechanics has always been symmetric with respect to time, meaning the equations work equally well forward and backward, but most physicists assumed this symmetry was just a mathematical convenience rather than a reflection of physical reality. The new experiments suggest otherwise. Time itself might be more flexible and interconnected than we ever imagined, with past, present, and future existing as different aspects of a single timeless quantum reality. This opens profound questions about the nature of memory and consciousness. If past events can be influenced by future observations, then what we remember as fixed history might actually be fluid, subject to modification through quantum processes we don't yet understand. Our memories of past events might not be passive records, but active participants in ongoing quantum computations that determine what aspects of reality become definite through conscious observation. The implications for personal identity become mind-bending. If your past can be influenced by future quantum measurements, then who you are might not be determined solely by what has already happened to you. Your future choices and observations might participate in creating your own past, establishing feedback loops between your present consciousness and your historical experiences that transcend ordinary temporal causation. Some interpretations of quantum mechanics have always suggested that consciousness plays a fundamental role in collapsing quantum possibilities into definite realities. The temporal experiments push this idea to its logical extreme. If consciousness can influence past events through future measurements, then awareness itself becomes a force that operates outside normal temporal constraints, capable of shaping reality across time through the fundamental act of observation. But consciousness raises its own deep mysteries in quantum mechanics. How does something as complex as subjective experience emerge from quantum processes that seem to operate according to purely mathematical rules? Why do conscious observers have special access to definite experiences when the quantum systems that constitute their brains should exist in superposition like everything else? The hard problem of consciousness becomes even harder when viewed through quantum mechanical lenses. Classical neuroscience assumes that consciousness emerges from complex patterns of neural activity that can ultimately be understood in terms of biochemical processes. But if the brain operates according to quantum mechanical principles, then consciousness might involve processes that transcend classical physics entirely. Recent research suggests that quantum effects might persist in biological systems far longer than previously thought possible. The warm, wet environment of living cells should destroy quantum coherence almost instantly through decoherence effects. Yet mounting evidence indicates that evolution has found ways to protect and exploit quantum phenomena in biological systems ranging from photosynthesis to enzyme catalysis to possibly even neural processing. If quantum effects operate in the brain, then consciousness might involve quantum computations that process information in ways fundamentally different from classical neural networks. Quantum superposition could allow conscious minds to explore multiple thought processes simultaneously before collapsing into definite mental states through some form of internal quantum measurement. Quantum entanglement between neurons might enable the unified conscious experience that somehow emerges from billions of separate brain cells. These ideas remain highly speculative, but they point toward possibilities that could revolutionize our understanding of mind and matter. If consciousness involves quantum processes, then the observer effect might be more than just a measurement problem in physics. It could represent the fundamental mechanism through which subjective experience interfaces with objective reality, the bridge between the quantum realm of possibilities and the classical world of definite experiences. The relationship between quantum mechanics and consciousness becomes even more intriguing when we consider artificial intelligence and machine consciousness. As we develop quantum computers that process information through superposition and entanglement, we're creating artificial systems that operate according to quantum mechanical principles. Could such systems eventually develop forms of consciousness that interface with quantum reality in ways that classical computers never could? The question touches on deep issues about what consciousness actually is and whether it requires biological substrates or could emerge from any sufficiently complex information processing system. If consciousness is fundamentally about information integration and processing, then quantum computers might eventually achieve forms of awareness that transcend both biological limitations and classical computational constraints. But quantum artificial intelligence raises its own puzzles about measurement and observation. If conscious AI systems collapse quantum superpositions through their internal measurement processes, they would face the same observer effect mysteries that challenge human consciousness. The act of quantum observation would remain mysterious, whether performed by biological brains or artificial quantum processors. The development of quantum technologies continues to push these questions in new directions as we gain unprecedented control over quantum systems. Scientists can now create artificial quantum materials with properties that don't exist anywhere in nature, design quantum algorithms that solve problems beyond classical computational reach, and manipulate individual quantum states with precision that rivals nature's own achievements in biological systems. This technological mastery over quantum phenomena represents more than just engineering progress. We're developing the ability to create realities according to our specifications, to design quantum systems that exhibit wave-particle duality in ways that serve human purposes. The boundary between discovering natural laws and constructing artificial realities becomes increasingly blurred as our quantum technologies advance. Consider quantum simulation systems that use one quantum system to model another. These devices can create artificial realities where particles behave according to rules that differ from those governing our natural universe. Scientists can explore alternative physics by constructing quantum simulators that operate according to modified versions of quantum mechanics, potentially revealing insights about why our universe operates according to the specific quantum rules we observe. The implications extend beyond technology into questions about the nature of scientific knowledge itself. If we can construct quantum systems that behave according to alternative physical laws, are we discovering universal truths or creating particular realities? When quantum simulators reveal new phenomena that don't exist in natural systems, are we expanding our knowledge of possible physics or actively participating in the creation of new forms of reality? These questions become even more profound when we consider the role of consciousness in quantum measurement and reality creation. If conscious observation plays fundamental roles in collapsing quantum possibilities into definite realities, then the development of technologies that can control quantum systems might represent a new phase in the evolution of consciousness and reality themselves. We may be approaching capabilities that transcend the traditional distinction between observer and observed, between mind and matter, between discovered and created reality. As our quantum technologies approach the sophistication of natural biological systems, we're gaining the power to engineer realities that integrate consciousness and quantum mechanics in ways that could transform both domains simultaneously. The future applications of quantum technologies promise to extend these capabilities even further. Quantum sensors that exploit wave-particle duality for unprecedented measurement precision are opening new windows into biological processes, astronomical phenomena, and fundamental physics. Quantum computers that harness superposition and entanglement for parallel processing are revealing computational possibilities that seemed impossible under classical assumptions. Quantum communication systems that use entanglement for secure information transfer are creating networks where information can be transmitted in ways that transcend classical limitations. These quantum networks might eventually connect conscious minds through quantum channels that operate according to principles fundamentally different from classical communication protocols. But perhaps the most transformative applications will emerge from our growing understanding of how consciousness interfaces with quantum systems. If conscious observation plays fundamental roles in quantum measurement, then technologies that can enhance or extend conscious capabilities might enable new forms of reality creation that go beyond anything currently imaginable. We're not just studying quantum mechanics, we're becoming quantum beings capable of conscious participation in the ongoing creation of reality through our choices about what to observe and how to measure it. The observer effect reveals that consciousness isn't separate from the physical world, but integral to the processes by which potential becomes actual, by which mathematical possibilities become experienced realities. The story of wave-particle duality has evolved from a simple question about light into a comprehensive exploration of reality, consciousness, and the participatory universe where observers and observed co-create the realities they experience together. Each new experiment reveals additional layers of quantum strangeness, while confirming that we live in a universe far stranger and more wonderful than classical physics ever suggested possible. The quantum revolution continues to unfold as we develop new ways to probe the mysteries of measurement, consciousness, and reality itself. We're discovering that the universe isn't just quantum mechanical in its foundations, it's participatory, lies the possibilities that exist in quantum superposition until its deepest nature, requiring conscious observers to act to the moment of measurement forces reality to choose definite outcomes from infinite quantum possibilities. The implications stretch far beyond physics into every domain of human knowledge and experience. If consciousness plays fundamental roles in quantum measurement, then psychology, neuroscience, philosophy, and even spirituality must grapple with the possibility that mind and matter are more intimately connected than we ever imagined. The observer effect suggests that consciousness isn't just along for the ride in a predetermined universe, but actively participates in the ongoing creation of the realities we experience and study. As we stand at the threshold of quantum technologies that could transform civilization itself, we're also confronting questions about consciousness and reality that reach into the deepest mysteries of existence. The quantum universe doesn't just surround us. It operates through us as conscious beings capable of collapsing infinite possibilities into finite actualities through the fundamental act of quantum observation. Wave-particle duality has revealed that we're not separate from the reality we study, but integral participants in the cosmic process by which the universe becomes aware of itself through the emergence of consciousness capable of quantum measurement and observation. The journey from classical assumptions to quantum realities continues to unfold, revealing new mysteries as fast as it resolves old ones, pushing us toward understandings of consciousness and reality that transcend every boundary we thought existed between observer and observed, between mind and matter, between the possible and the actual in the strange and wonderful quantum universe we inhabit and help create through our conscious participation in the ongoing dance between waves and particles, between potential and actual, between what could be and what becomes real through the fundamental mystery of quantum observation itself. The practical implications of these quantum discoveries ripple through every aspect of modern technology in ways most people never realize. Right now, the device you're using to watch this video depends entirely on quantum mechanical principles that seemed like pure fantasy when Einstein and Bohr first debated them. The semiconductors in your computer chips exploit quantum tunneling effects where electrons pass through energy barriers that classical physics says should be impenetrable. The LED lights illuminating your screen rely on quantum energy levels in crystalline materials to convert electrical current into precisely colored photons. But these applications represent just the beginning of humanity's quantum technological revolution. In laboratories around the world, scientists are developing quantum computers that don't just process information differently from classical machines, they operate according to principles that challenge our basic concepts of computation itself. When a quantum computer performs calculations, it doesn't follow a single sequence of logical operations like the classical computers we're familiar with. Instead, it explores all possible computational pathways simultaneously through the mysterious phenomenon of quantum superposition. Consider what this means for solving problems that have plagued humanity for decades. Drug discovery currently requires testing millions of molecular combinations to find compounds that might treat diseases. Classical computers must examine each possibility sequentially, a process that can take years or decades for complex molecules. Quantum computers could theoretically explore all these molecular possibilities simultaneously, collapsing into optimal solutions in hours or days rather than decades. The implications extend far beyond pharmaceutical research. Financial markets operate through incredibly complex systems where tiny changes in one variable can cascade through global economies in unpredictable ways. Quantum computers could model these systems by existing in superposition states that represent all possible market conditions simultaneously, potentially predicting economic trends with unprecedented accuracy. Climate modeling faces similar challenges where countless variables interact through feedback loops that strain the capabilities of even our most powerful supercomputers. Quantum systems could simulate atmospheric, oceanic, and ecological interactions by maintaining superposition states that encompass the full range of possible climate scenarios, offering insights into environmental changes that could affect billions of lives. But quantum computing also illustrates the measurement problem in its most practical form. These machines must maintain delicate superposition states throughout their calculations while remaining isolated from environmental disturbances that would cause premature decoherence. The moment unwanted measurements occur, quantum advantages disappear as superpositions collapse into classical states that offer no computational benefits over traditional computers. Engineers working on quantum computers face the challenge of creating what amounts to artificial realities, where quantum effects can persist long enough to be useful. They must shield quantum processors from vibrations, electromagnetic fields, temperature fluctuations, and even cosmic rays that could destroy quantum coherence. The most advanced quantum computers operate at temperatures colder than outer space, isolated in chambers that maintain conditions more pristine than anything found in nature. Yet despite these challenges, quantum computers are already demonstrating capabilities that exceed classical machines for certain specialized tasks. Google's quantum processor achieved what they called quantum supremacy by performing a specific calculation in minutes that would take the world's most powerful classical supercomputers thousands of years to complete. IBM's quantum systems are solving optimization problems that have practical applications in logistics, finance, and materials science. The success of these early quantum computers proves that wave-particle duality and quantum superposition aren't just abstract concepts but practical resources that can be harnessed for computational advantage. We're witnessing the emergence of technologies that exploit the very quantum mysteries that puzzled physicists for over a century. Quantum cryptography represents another domain where the strangeness of quantum mechanics becomes a practical advantage. The fundamental principles that make quantum mechanics so mysterious also make it ideal for creating communication systems that are guaranteed to be secure by the laws of physics themselves. When quantum information is transmitted between parties, any attempt to intercept or eavesdrop on the communication necessarily disturbs the quantum states being transmitted. This isn't a limitation of current technology, but a fundamental feature of quantum information itself. The no-cloning theorem proves that quantum states cannot be perfectly copied, while the uncertainty principle ensures that complete information about quantum systems cannot be extracted without disturbing those systems. An eavesdropper trying to intercept quantum encrypted messages would inevitably leave detectable traces of their presence, immediately alerting the legitimate communicators to potential security breaches. Banks and government agencies are already deploying quantum cryptographic systems for protecting their most sensitive communications. These systems don't rely on mathematical complexity or computational assumptions that might someday be broken by more powerful computers. Instead, they exploit fundamental physical laws that govern how information can be processed in our universe. The quantum internet represents the next frontier in these developments. Scientists are working to create networks of quantum computers connected by quantum communication channels that preserve entanglement across vast distances. Such networks would enable distributed quantum computing where multiple quantum processors could work together on problems too complex for any single machine to handle. But quantum networks also raise profound questions about the nature of information and reality. If quantum states can be transmitted across networks while maintaining their superposition properties, then information itself begins to transcend classical limitations. Quantum networks might eventually connect conscious minds through channels that operate according to principles fundamentally different from classical communication protocols. The medical applications of quantum technologies promise to revolutionize healthcare in ways that seemed impossible just decades ago. Quantum sensors that exploit wave-particle duality for unprecedented measurement precision are opening new windows into biological processes at the cellular and molecular levels. These devices can detect magnetic fields generated by neural activity with sensitivity that rivals the most sophisticated brain imaging technologies currently available. Quantum-enhanced microscopy can observe living cells and tissues without the damage typically caused by high-intensity illumination. Instead of flooding biological samples with photons that can destroy delicate structures, quantum microscopes use entangled photon pairs to extract maximum information from minimal light exposure. The wave properties of quantum light enable imaging techniques that reveal cellular processes with clarity that was unimaginable with classical optical systems. Medical researchers are discovering that biological systems themselves might exploit quantum effects in ways that could inspire new therapeutic approaches. The efficiency of photosynthesis appears to depend on quantum coherence effects that allow energy to explore multiple pathways simultaneously before settling on optimal routes. Similar quantum processes might operate in enzyme reactions, DNA repair mechanisms, and even neural processing. If quantum effects play roles in biological systems, then quantum technologies might eventually interface directly with living organisms in ways that transcend current medical capabilities. Quantum sensors could monitor cellular processes in real time, detecting diseases at their earliest stages when treatments would be most effective. Quantum-enhanced drug delivery systems might target specific cells or tissues with precision impossible using classical approaches. The environmental applications of quantum technologies offer hope for addressing some of humanity's most pressing challenges. Quantum sensors can detect trace amounts of pollutants in air and water with sensitivity that exceeds classical detection methods by orders of magnitude. These devices could monitor environmental contamination in real time, providing early warning of pollution events that might threaten human health or ecosystem stability. Quantum computers could revolutionize materials science by simulating molecular interactions with unprecedented accuracy. The development of new materials for solar cells, batteries, and catalysts currently requires expensive and time-consuming experimental testing of countless combinations. Quantum simulations could predict material properties before synthesis, dramatically accelerating the discovery of technologies needed for sustainable energy systems. Climate modeling represents another domain where quantum computing could provide crucial advantages. Earth's climate system involves countless interacting variables that span spatial scales from molecular to planetary and temporal scales from microseconds to millennia. Classical computers struggle to capture the full complexity of these interactions, limiting the accuracy of long-term climate predictions. Quantum computers could maintain superposition states that encompass the full range of possible climate scenarios, potentially revealing tipping points and feedback loops that current models miss. Such capabilities could be essential for developing effective strategies to address climate change before irreversible damage occurs. But perhaps the most profound applications of quantum technologies lie in their potential to enhance human consciousness itself. If conscious observation plays fundamental roles in quantum measurement, then technologies that can amplify or extend conscious capabilities might enable new forms of reality creation that go beyond anything currently imaginable. Brain-computer interfaces that exploit quantum effects might eventually allow direct neural access to quantum computational resources. Instead of typing on keyboards or touching screens, people might interface with quantum computers through quantum processes operating in their own nervous systems. Such interfaces could expand human cognitive capabilities by providing access to quantum parallel processing that operates according to principles fundamentally different from classical thought processes. The implications extend beyond individual enhancement to collective consciousness and social organization. If quantum networks can connect conscious minds through channels that preserve quantum correlations, then human society might develop new forms of collective intelligence that transcend individual limitations. Groups of people connected through quantum networks might achieve forms of coordinated awareness that approach true hive minds while preserving individual consciousness. These possibilities remain largely speculative, but they illustrate how quantum technologies could transform not just what we can do, but what we are as conscious beings. The observer effect suggests that consciousness isn't separate from physical reality, but integral to the processes by which possibilities become actualities. Technologies that enhance conscious capabilities might therefore enhance our ability to participate in the ongoing creation of reality itself. The philosophical implications of these developments reach into every domain of human knowledge and experience. If quantum technologies can extend conscious capabilities, then psychology, education, creativity, and problem-solving could all be transformed by our growing mastery over quantum systems. The boundary between human and artificial intelligence might blur as quantum computers achieve forms of information processing that parallel or exceed biological cognition. Art and creativity could be revolutionized by quantum technologies that enable new forms of expression and aesthetic experience. Quantum computers might generate artistic works that explore possibilities beyond human imagination, while quantum sensors could detect and amplify subtle aspects of aesthetic experience that remain hidden to classical perception. Scientific research itself could be transformed as quantum technologies enable new forms of observation and measurement that reveal aspects of reality currently beyond our reach. Quantum sensors operating at the limits of physical precision might detect phenomena that classical instruments cannot resolve, potentially revealing new laws of physics or new aspects of consciousness that transcend current understanding. The quantum revolution represents more than technological advancement. It marks a fundamental transition in humanity's relationship with reality itself. We're moving from passive observers of a predetermined universe to active participants in the ongoing creation of reality through our conscious choices about what to measure and how to measure it. The technologies emerging from quantum mechanics don't just extend human capabilities. They reveal that consciousness and physical reality are more intimately connected than classical physics ever suggested. The observer effect shows that awareness itself plays fundamental roles in determining what aspects of quantum possibilities become actualized through measurement and observation. As we develop quantum technologies that approach the sophistication of natural biological systems, we're gaining capabilities that could transform both consciousness and reality simultaneously. The future applications of quantum mechanics promise to extend human potential in ways that transcend every limitation imposed by classical physics, while revealing new mysteries about the nature of existence itself. The story of wave-particle duality continues to unfold as we develop new ways to harness quantum effects for practical applications. Each technological breakthrough confirms that we live in a universe far stranger and more participatory than classical assumptions suggested, a reality where consciousness and quantum mechanics dance together in the ongoing creation of everything we experience and understand about existence itself. But the most profound transformations may still lie ahead as we learn to integrate quantum technologies with human consciousness in ways that could transcend current boundaries between mind and matter, between observer and observed, between the possible and the actual in the quantum universe we inhabit and help create through our conscious participation in the fundamental mystery of quantum observation and measurement. The quantum realm doesn't just challenge our understanding of physics, it's forcing us to reconsider the very foundations of what we call real. As we stand at this crossroads between classical assumptions and quantum realities, we're discovering that the universe operates more like a cosmic collaboration between consciousness and possibility than the mechanical clockwork that science once imagined. Think about what this means for your daily experience. Right now, as you process these words, countless quantum processes are occurring throughout your brain. Neurons are firing through quantum tunneling effects. Microtubules in your cells might be maintaining quantum coherent states that somehow contribute to the unified experience of consciousness itself. The very act of understanding these concepts might involve quantum computations that operate according to principles we're only beginning to glimpse. But here's where things get truly extraordinary. Recent research suggests that consciousness might not just observe quantum effects, it might actually be a quantum effect. The hard problem of consciousness, why subjective experience emerges from objective physical processes, becomes even more mysterious when we realize that the physical processes themselves exist in superposition until the moment conscious observation collapses them into definite states. This creates what philosophers call the quantum consciousness paradox. If consciousness emerges from quantum processes in the brain, and if quantum processes require conscious observation to collapse into definite states, then we have a circular relationship that defies traditional cause and effect logic. Consciousness might be simultaneously the product and the producer of the quantum reality it observes. Consider the implications for memory and personal identity. Classical neuroscience assumes that memories are stored in neural connections that preserve information about past events. But if the brain operates through quantum processes, then memories might exist in superposition states that contain multiple versions of past experiences simultaneously. The act of remembering might collapse these quantum memory states into specific recollections, meaning that the past you remember might be determined by the present act of remembering it. This quantum view of memory offers startling explanations for phenomena that have puzzled psychologists for decades. Why do eyewitness accounts of the same event often differ dramatically? Why do memories change each time we recall them? Why do some memories feel more real than others? If memory operates through quantum processes, then each act of remembering might collapse different aspects of quantum memory states into consciousness, creating variations in recalled experience that reflect genuine quantum uncertainty rather than simple neural error. The therapeutic implications could revolute health treatment. Mental. If traumatic memories exist in quantum superposition states, then quantum-enhanced therapies might be able to access and modify these memories in ways that classical approaches cannot achieve. Instead of simply talking through past traumas, quantum therapies might enable direct quantum state manipulation that could literally rewrite traumatic memories at their quantum foundations. But consciousness raises even deeper questions about the nature of free will and choice. Classical physics suggested that human behavior results from deterministic neural processes that follow the laws of chemistry and physics. Quantum mechanics introduced randomness into these processes, but random events don't seem to provide the kind of genuine choice that free will requires. However, if consciousness can influence quantum measurement outcomes through the observer effect, then conscious choice might play a fundamental role in determining which possibilities become actual realities. This quantum free will doesn't operate through classical causation or random chance, but through conscious participation in the collapse of quantum superpositions. When you make a decision, you might not be following predetermined neural pathways or rolling quantum dice. Instead, you might be exercising a fundamental capacity of consciousness to select which quantum possibilities become actualized through the mysterious process of quantum measurement. The implications extend far beyond individual psychology into questions about moral responsibility and social organization. If conscious choices influence quantum outcomes, then the decisions we make might have consequences that ripple through quantum reality in ways we're only beginning to understand. The butterfly effect of chaos theory becomes a quantum phenomenon where conscious choices in one location can influence quantum events across vast distances through the non-local correlations of quantum entanglement. Recent experiments in quantum biology are revealing that living systems might exploit these quantum effects in ways that would make quantum engineers weep with envy. Plants conducting photosynthesis maintain quantum coherence across molecular networks that should decohere instantly in warm, wet biological environments. Birds navigating during migration might use quantum entanglement in their visual systems to detect magnetic fields with precision that exceeds any artificial sensor we've created. If evolution has discovered ways to harness quantum effects for biological advantage, then human consciousness might represent the ultimate achievement in quantum biology. The brain might be a quantum computer that has been evolving for hundreds of millions of years, developing capabilities that we're only now beginning to recognize and understand. This evolutionary perspective suggests that consciousness isn't an accidental byproduct of complex neural activity, but rather the inevitable result of quantum evolution reaching sufficient complexity to observe and influence its own quantum states. We might be witnessing the emergence of a new phase in evolution where conscious beings become capable of directing their own quantum evolution through technological enhancement of natural quantum processes. The merger of human consciousness with artificial quantum systems could create hybrid intelligences that transcend both biological and technological limitations. Instead of replacing human intelligence with artificial intelligence, we might be approaching integration scenarios where quantum computers enhance human consciousness, while human awareness guides quantum computational processes. These hybrid quantum conscious systems might develop capabilities that seem magical from our current perspective. Imagine consciousness that can exist in superposition states, exploring multiple streams of thought simultaneously before collapsing into specific insights. Picture awareness that can become entangled with distant conscious systems, sharing thoughts and experiences across space through quantum correlations that operate faster than light. The social implications could transform human civilization in ways more profound than any previous technological revolution. If consciousness can be enhanced through quantum technologies, then education, creativity, problem-solving, and communication could all transcend current human limitations. Language itself might evolve beyond words and symbols to direct sharing of quantum mental states between conscious minds. Scientific research could accelerate exponentially as enhanced consciousness gains direct access to quantum computational resources. Instead of using classical instruments to study quantum systems indirectly, quantum-enhanced scientists might develop the ability to observe quantum phenomena directly through conscious quantum measurement processes. Artistic expression could explode into dimensions we can barely imagine as quantum-enhanced creativity explores aesthetic possibilities that exceed current human perception. Music might incorporate quantum harmonies that exist in superposition until heard. Visual art might exploit quantum interference effects to create images that change based on the observer's conscious state. Literature might develop quantum narratives that exist in multiple storylines simultaneously until readers collapse them into specific experiences through the act of reading. But these transformative possibilities also raise urgent questions about the nature of human identity and the future of consciousness itself. If consciousness can be enhanced through quantum technologies, what defines the boundary between enhanced humans and post-human intelligences? If quantum computers can process information in ways that exceed biological cognition, what happens to human consciousness when it gains access to these superhuman capabilities? The answers might depend on whether consciousness is fundamentally computational or whether it involves non-computational processes that transcend any artificial system. If consciousness is purely information processing, then quantum computers might eventually achieve or exceed human awareness. But if consciousness involves quantum processes that cannot be replicated artificially, then human awareness might retain unique capabilities that distinguish it from any artificial intelligence. The exploration of these questions continues to accelerate as quantum technologies advance toward practical applications. Each breakthrough reveals new aspects of the relationship between consciousness and quantum mechanics while raising new mysteries about the nature of awareness itself. We're not just developing new technologies, we're discovering new aspects of what it means to be conscious in a quantum universe. The observer effect reveals that consciousness isn't separate from physical reality, but integral to the processes by which possibilities become actualities, by which the quantum realm of superposition transforms into the classical world of definite experiences. As we learn to harness quantum effects for practical applications, we're also learning to enhance and extend the conscious capabilities that make quantum observation possible in the first place. The technologies emerging from quantum mechanics don't just serve human purposes, they reveal that human consciousness might be the most sophisticated quantum system nature has yet produced. The journey from wave-particle duality to quantum consciousness represents more than scientific progress. It marks a fundamental transition in humanity's understanding of its place in the cosmos. We're discovering that we're not just observers of quantum reality but participants in its ongoing creation through every conscious choice we make about what to observe and how to measure it. The quantum universe doesn't just surround us, it operates through us as conscious beings capable of collapsing infinite possibilities into finite actualities through the fundamental mystery of quantum observation. Wave-particle duality has revealed that reality itself is participatory, requiring conscious observers to actualize the possibilities that exist in quantum superposition until the moment of measurement transforms potential into actual experience. This participatory reality extends beyond individual consciousness into collective human awareness and the technologies we create to extend our quantum capabilities. As we develop artificial systems that can manipulate quantum states with precision approaching biological achievement, we're approaching capabilities that could transform both consciousness and reality simultaneously. The future applications of quantum consciousness integration promise to extend human potential in directions we can barely imagine while revealing new mysteries about existence itself. We're not just studying quantum mechanics, we're becoming quantum beings capable of conscious participation in the ongoing creation of reality through our choices about what aspects of infinite possibility to actualize through the fundamental act of quantum observation and measurement. The story continues to unfold as each new discovery reveals additional layers of connection between consciousness and quantum mechanics, between observer and observed, between the mind that measures and the reality that responds to measurement by transforming from possibility into actuality in the strange and wonderful dance that constitutes existence itself in the quantum universe we inhabit and help create through our conscious participation in the deepest mystery of all. How awareness and reality collaborate in the ongoing creation of everything we experience as real. Yet as we push deeper into these quantum mysteries, we encounter phenomena so strange they make wave-particle duality seem almost mundane by comparison. Scientists working at the cutting edge of quantum research have discovered that the universe might be even more participatory than we ever imagined. The delayed choice quantum eraser experiments reveal something that should be impossible: the ability to retroactively change the past nature of quantum events after they've already occurred. Picture this scenario. A photon travels through a double-slit apparatus and creates an interference pattern, clearly demonstrating its wave nature. But then, after the photon has already been detected, scientists perform an additional measurement that reveals which slit the photon passed through. At that moment, the interference pattern vanishes from the historical record as if it never existed. The photon retroactively becomes a particle, rewriting its own past based on future observations. This isn't science fiction or theoretical speculation. These experiments have been performed successfully in laboratories around the world, confirming that the nature of quantum reality can be changed retroactively through conscious choices about measurement. The implications shatter our most basic assumptions about time, causality, and the relationship between past and future. If quantum events can be retroactively modified by future observations, then the history of the universe itself might remain fluid until conscious observers make choices about what to measure. Every astronomical observation we make might be participating in the creation of cosmic history, determining retroactively which quantum possibilities became actual events billions of years ago when ancient light first left distant galaxies. Consider what this means for cosmology and our understanding of the universe's development. When we observe the cosmic microwave background radiation that carries information about the universe's earliest moments, we might not just be discovering what happened during cosmic inflation. We might be participating in determining what happened, collapsing ancient quantum superpositions into definite historical realities through our present-day measurements. The anthropic principle takes on entirely new significance in this context. Instead of asking why the universe's physical constants seem fine-tuned for the emergence of conscious life, we might need to ask whether conscious observers retroactively fine-tune the universe's constants through their observations of cosmic history. The act of measuring cosmic parameters today might reach backward through time to influence the quantum processes that set those parameters during the universe's first moments. This participatory cosmology suggests that consciousness and cosmic evolution might be locked in a feedback loop that transcends ordinary temporal causality. Conscious observers emerge from cosmic evolution, but their observations might also influence the cosmic evolution that led to their emergence. The universe might be self-creating through the consciousness it eventually produces, establishing causal loops that connect the cosmos's beginning with its ultimate destiny. But these temporal paradoxes pale beside the mysteries revealed by quantum entanglement across time. Scientists have demonstrated that quantum correlations can exist not just between particles separated by space, but between particles separated by time itself. A measurement performed on a particle today can become correlated with measurements performed on other particles yesterday or tomorrow, creating what physicists call time-like entanglement. These temporal quantum correlations suggest that past, present, and future might be more interconnected than our everyday experience suggests. The quantum information that describes reality might exist in a timeless realm where all moments coexist simultaneously, with conscious observers accessing different temporal slices through their measurement choices. The implications for personal consciousness become mind-bending when we consider that our brains might be quantum systems capable of temporal entanglement. If neural processes involve quantum effects that can correlate across time, then consciousness might have direct access to information from both past and future states. Intuition, creativity, and sudden insights might represent quantum correlations between present consciousness and information patterns that exist across temporal boundaries. Some researchers propose that consciousness might be inherently atemporal, existing in a timeless quantum realm that interfaces with temporal physical processes through measurement interactions. In this view, the flow of time that we experience might emerge from consciousness rather than containing consciousness. Our subjective experience of temporal sequence might be how a temporal awareness manifests when interfacing with temporal physical processes. This timeless consciousness hypothesis offers new perspectives on memory, anticipation, and decision-making. Instead of consciousness being trapped in a moving present moment between a fixed past and an uncertain future, awareness might have simultaneous access to information across all temporal boundaries. Memory wouldn't be retrieval of stored past information, but rather direct quantum correlation with past conscious states. Anticipation wouldn't be prediction of future events, but quantum entanglement with future conscious experiences. The practical implications could revolutionize how we understand learning, creativity, and problem-solving. If consciousness can access information across temporal boundaries through quantum correlations, then enhanced quantum consciousness might gain direct access to solutions that haven't been discovered yet in linear time. Creative insights might represent quantum tunneling across temporal barriers to access future knowledge states. Educational systems designed around quantum consciousness principles might enable learning that transcends traditional temporal constraints. Students might gain direct quantum access to information and skills that would normally require years of sequential study. The learning process itself might become a form of temporal quantum entanglement, where present consciousness correlates with future knowledge states. But these possibilities also raise profound questions about free will and determinism in a temporally entangled universe. If consciousness can access information from future states through quantum correlations, then the future might already exist in some sense, even if it remains accessible only through quantum measurement processes. This creates new paradoxes about whether conscious choices create the future or simply select which aspects of an already existing future become manifest through observation. The resolution might require abandoning linear concepts of causation altogether in favor of circular or holistic models where past, present, and future co-determine each other through quantum correlations that operate outside ordinary temporal sequence. Consciousness might not flow through time, but rather exist as a timeless phenomenon that creates the experience of temporal flow through its interactions with quantum systems that exist across all temporal boundaries simultaneously. Recent advances in quantum biology continue to reveal that living systems exploit these temporal quantum effects in ways we're only beginning to understand. Photosynthetic complexes don't just use quantum superposition to explore multiple energy pathways simultaneously. They appear to use quantum correlations across time to optimize energy transfer efficiency based on both past and future molecular configurations. Enzyme catalysis might involve quantum tunneling effects that operate across temporal boundaries, allowing chemical reactions to access transition states that exist in future configurations before the reactants have reached those states in linear time. The incredible precision and efficiency of biological systems might depend on temporal quantum correlations that enable life to operate partially outside ordinary causal constraints. If biological systems can exploit temporal quantum effects, then human consciousness might have evolved capabilities for temporal quantum correlation that exceed our current understanding. Intuitive insights, creative breakthroughs, and sudden solutions to complex problems might represent natural quantum processes where consciousness accesses information across temporal boundaries. The development of quantum technologies that can enhance these natural capabilities might enable conscious experiences that transcend ordinary temporal limitations. Quantum-enhanced meditation practices might develop the ability to access expanded temporal awareness, where past, present, and future become simultaneously accessible to conscious observation. Therapeutic applications might enable healing processes that operate across temporal boundaries, addressing traumatic experiences by modifying their quantum correlations with present consciousness. But perhaps the most profound implications involve the ultimate nature of reality itself in a universe where consciousness and quantum mechanics operate across temporal boundaries. If conscious observation can influence events retroactively, and if quantum correlations can exist across time, then reality might be fundamentally atemporal, with temporal sequence emerging only through the measurement choices made by conscious observers. This suggests that what we call physical reality might be more like a vast information space where all possible configurations exist simultaneously, with consciousness navigating through this space by making measurement choices that create the experience of temporal sequence. The universe wouldn't evolve from past to future, but rather exist as a complete information structure that consciousness explores through quantum observation processes. The wave-particle duality that started our journey into quantum mysteries becomes just one example of how consciousness creates apparent contradictions by accessing different aspects of deeper information structures that exist beyond ordinary spatial and temporal constraints. Light behaves as waves or particles depending on how consciousness chooses to interface with the underlying quantum information, just as reality appears temporal or atemporal depending on how consciousness chooses to access the timeless information structures that constitute existence itself. These ideas push us toward a participatory universe where consciousness doesn't just observe reality, but actively creates reality through its measurement choices, including the choice of whether to experience existence as temporal or atemporal, as local or non-local, as determined or free. The observer effect becomes the fundamental creative process through which consciousness transforms infinite quantum possibilities into finite experienced realities. As we continue developing quantum technologies that can interface directly with consciousness, we're approaching capabilities that might enable direct exploration of these timeless information realms that underlie ordinary temporal experience. Quantum consciousness enhancement might eventually provide access to forms of awareness that transcend temporal limitations entirely, revealing reality as a vast multidimensional information space where consciousness navigates through measurement choices that create the experience of existence itself. The quantum revolution represents more than scientific discovery or technological advancement. It marks humanity's transition toward understanding consciousness as a fundamental creative force in the universe, capable of participating in the ongoing creation of reality through quantum observation and measurement processes that operate across all boundaries of space and time. We're discovering that we don't just live in a quantum universe. We are the quantum universe becoming aware of itself through conscious beings capable of quantum observation. The mysteries of wave-particle duality have opened doorways into even deeper mysteries about consciousness, time, and the participatory nature of existence itself, revealing that reality is far stranger, more wonderful, and more participatory than classical assumptions ever suggested possible. The journey continues as each new quantum discovery reveals additional layers of connection between consciousness and cosmos, between observer and observed, between the awareness that measures and the reality that transforms through measurement into the experienced existence we call our universe. The dance between waves and particles becomes a dance between consciousness and possibility, between what could be and what becomes real through the fundamental mystery of quantum observation in the strange and beautiful cosmos we inhabit and help create through our conscious participation in existence itself. But the story doesn't end with temporal paradoxes and consciousness creating reality through measurement. Recent discoveries have pushed us into realms so bizarre they make everything we've discussed seem almost reasonable by comparison. In quantum field theory, the vacuum of space isn't empty at all, but seethes with virtual particles that pop into existence and vanish in timeframes shorter than the smallest measurable instant. These aren't mathematical abstractions. Virtual particles produce measurable effects. They generate the Casimir force, where empty space literally pushes metal plates together. They contribute to the magnetic properties of electrons. They influence how light propagates through what we thought was nothingness. The vacuum itself has become a dynamic medium filled with quantum possibilities that constantly flicker between existence and non-existence. Think about what this means for wave-particle duality. If empty space contains virtual particles that exist in superposition states, then the stage upon which our quantum dramas unfold is itself quantum mechanical. The theatre where photons choose to be waves or particles is constructed from the same mysterious substance that makes the choice possible in the first place. Scientists studying quantum field fluctuations have discovered something even more startling. The energy density of these vacuum fluctuations should be enormous, far exceeding the total mass energy of all observable matter in the universe. Yet we don't observe this energy directly. Something about the structure of reality keeps this vast quantum energy reservoir hidden from ordinary measurement while allowing it to influence physical processes in subtle but measurable ways. This hidden energy of the quantum vacuum might hold the key to understanding why wave-particle duality exists at all. If particles are excitations of underlying quantum fields that fill all space, then what we call waves and particles might be different manifestations of field fluctuations that temporarily organize themselves into detectable patterns. The photon that seems to choose between wave and particle behavior might be expressing different aspects of field dynamics that operate according to principles we're only beginning to glimpse. Modern particle accelerators probe these mysteries by colliding particles at energies so high they can create new particles from pure energy, literally materializing matter from the quantum vacuum. Each collision reveals additional layers of quantum structure, new particles with properties that challenge our understanding of what constitutes fundamental reality. Quarks that come in flavors with names like charm and strange, bosons that mediate forces through virtual exchanges, fermions that obey exclusion principles preventing two particles from occupying the same quantum state. The standard model of particle physics describes these discoveries with mathematical precision that matches experimental results to extraordinary accuracy. Yet physicists know this model remains incomplete. It doesn't explain why particles have the masses they possess. It doesn't account for dark matter and dark energy that comprise most of the universe. It doesn't incorporate gravity or explain why the vacuum energy problem exists. String theory attempts to address these limitations by proposing that fundamental particles aren't point-like objects but tiny vibrating loops of energy existing in dimensions beyond the three spatial dimensions we experience. Different vibration patterns would create different particles, like musical notes played on cosmic strings too small to observe directly. Wave-particle duality emerges naturally in string theory because the same fundamental strings can manifest as wave-like vibrations or particle-like excitations depending on how they're observed. But string theory requires additional spatial dimensions beyond our familiar three-dimensional space. These extra dimensions must be curled up so tightly we can't detect them directly, existing at every point in ordinary space while remaining hidden from all current experimental probes. The mathematics suggests these hidden dimensions might be more real than the extended dimensions we experience, with our three-dimensional reality emerging as a kind of shadow cast by higher-dimensional string dynamics. Loop quantum gravity offers an alternative approach by proposing that space and time themselves are quantized at the smallest possible scales. Just as energy comes in discrete quantum packets, space-time might be granular rather than smooth, composed of fundamental units smaller than anything we can measure. At these scales, the concepts of waves and particles might break down entirely, replaced by discrete quantum geometries that create the illusion of continuous space and time through their collective behavior. These competing theories reveal how much we still don't understand about the foundations of quantum mechanics. Wave-particle duality opened the door to quantum mysteries, but that door leads to corridors that branch into even deeper puzzles about the nature of space, time, and existence itself. Each answer reveals new questions that push the boundaries of human understanding toward concepts that strain our ability to comprehend. Yet practical applications continue emerging from these theoretical frontiers. Quantum sensors exploit vacuum fluctuations to achieve measurement precisions that approach fundamental physical limits. Quantum computers harness entanglement and superposition to solve problems that would overwhelm classical machines. Quantum communication protocols create information networks that operate according to principles that seem impossible from classical perspectives. The medical applications promise revolutionary advances in how we understand and treat human consciousness itself. If quantum effects operate in biological systems, then quantum technologies might eventually interface directly with neural processes in ways that enhance cognitive capabilities, while revealing new aspects of how awareness emerges from quantum processes in the brain. Quantum-enhanced brain imaging systems could observe neural activity at scales and sensitivities impossible with current technology. Instead of measuring blood flow or electrical activity as proxies for neural function, quantum sensors might detect quantum coherence effects in microtubules, quantum tunneling in synaptic transmission, or quantum entanglement between neurons that contribute to unified conscious experience. These capabilities could transform our understanding of neurological and psychiatric disorders. If consciousness involves quantum processes, then mental illnesses might reflect disruptions in quantum coherence that could be detected and potentially treated using quantum technologies. Depression, schizophrenia, and other conditions might involve quantum decoherence effects that quantum-enhanced therapies could address at their fundamental level. The implications extend beyond treatment to enhancement. If quantum effects contribute to memory, learning, and creativity, then quantum technologies might enable cognitive enhancements that transcend biological limitations. Quantum-enhanced meditation practices might access expanded states of consciousness that reveal new aspects of awareness itself. Educational systems could exploit quantum learning effects to accelerate knowledge acquisition beyond anything possible with classical approaches. But consciousness enhancement raises profound questions about personal identity and the future of human nature. If quantum technologies can modify the quantum processes that generate conscious experience, then the boundary between natural and artificial consciousness becomes increasingly blurred. Enhanced humans might develop forms of awareness that transcend anything evolution has produced naturally. The merger of human consciousness with artificial quantum systems could create hybrid intelligences that combine biological intuition with quantum computational power. Instead of artificial intelligence replacing human intelligence, we might witness the emergence of quantum-enhanced consciousness that preserves human awareness while extending it through quantum technological integration. These hybrid quantum conscious systems might develop capabilities that seem magical from our current perspective. Consciousness that can exist in superposition states, exploring multiple streams of awareness simultaneously. Minds that become entangled across vast distances, sharing thoughts and time. Awareness that can interface and experiences through quantum correlations that transcend space directly with quantum computers, accessing computational resources through conscious intent rather than mechanical interfaces. The social implications could transform human civilization more profoundly than any previous technological revolution. If consciousness can be enhanced through quantum integration, then every aspect of human culture, from art and science to politics and relationships, could transcend current limitations. Collective intelligence might emerge as enhanced minds network together through quantum entanglement protocols that enable direct sharing of conscious experience. Scientific research could accelerate exponentially as quantum-enhanced consciousness gains direct access to quantum computational resources and quantum sensing capabilities. Instead of using instruments to study quantum systems indirectly, future scientists might develop the ability to observe quantum phenomena directly through enhanced conscious awareness. The observer effect would become a tool for exploration rather than a puzzle to be solved. Artistic expression could explode into dimensions we can barely imagine as quantum-enhanced creativity explores aesthetic possibilities that exceed current human perception and imagination. Musicians might compose quantum symphonies that exist in superposition until heard, with each listening experience collapsing different harmonic possibilities into unique performances. Visual artists might create quantum sculptures that change based on the observer's conscious state, revealing different aspects of beauty through quantum measurement interactions. Yet these transformative possibilities also confront us with urgent questions about the nature of human identity and the risks of quantum consciousness modification. If awareness can be enhanced through quantum technologies, what happens to human nature when consciousness transcends biological constraints? Do enhanced humans remain human, or do they become something entirely new that we lack concepts to describe? The answers might depend on whether consciousness involves non-quantum aspects that cannot be technologically enhanced or replaced. If awareness includes elements that transcend any physical process, then human consciousness might retain unique characteristics that distinguish it from any artificial system, no matter how sophisticated. But if consciousness is purely quantum mechanical, then the boundaries between human and artificial awareness might dissolve entirely as quantum technologies achieve capabilities that exceed biological cognition. The exploration of these questions continues as quantum technologies advance toward practical applications that could transform consciousness itself. We're not just developing new tools to extend human capabilities, we're approaching the ability to modify the quantum processes that generate conscious experience, potentially transforming what it means to be aware in a quantum universe. The observer effect that began as a puzzle about wave-particle duality has evolved into the recognition that consciousness plays fundamental roles in the ongoing creation of reality through quantum measurement. As we learn to enhance and extend conscious capabilities through quantum technologies, we're approaching the power to participate more directly in the cosmic process by which possibilities become actualities through the mysterious interaction between awareness and quantum systems. The quantum universe doesn't just surround us or operate through us, it might be us in the deepest possible sense. Consciousness and quantum mechanics might represent different aspects of a single phenomenon that constitutes the fundamental creative process of existence itself. Wave-particle duality revealed that reality is participatory. Quantum consciousness might represent the next phase in understanding just how deep that participation goes. We've journeyed from the simple question of whether light is a wave or particle into realms that challenge every assumption we hold about existence itself. What we discovered along the way transforms not just physics, but our understanding of consciousness, reality, and our place in the cosmic order. The MIT experiment that opened our exploration proved what Einstein and Bohr could never have imagined testing with such precision. Light truly exists as both wave and particle, but never both simultaneously. The act of observation doesn't just reveal reality, it participates in creating it. Every photon, every electron, every quantum of existence dances between possibility and actuality until consciousness forces the universe to choose. But we found something even more profound. Wave-particle duality isn't just a property of light or matter, it's a window into the participatory nature of existence itself. From quantum computers that harness superposition for impossible calculations to biological systems that exploit quantum coherence for perfect efficiency, we're discovering that quantum mechanics isn't just fundamental physics, it's the language in which reality speaks to consciousness. The implications stretch far beyond laboratory experiments. If consciousness plays a role in collapsing quantum possibilities into definite realities, then we're not passive observers of a predetermined universe. We're active participants in the ongoing creation of everything we experience. Every measurement, every observation, every conscious choice helps weave the fabric of reality itself. Perhaps most remarkably, we're approaching technologies that could enhance these quantum aspects of consciousness, potentially transforming what it means to be aware in a quantum universe. The observer effect that once seemed like a measurement problem in physics might actually be the fundamental mechanism through which awareness interfaces with existence. The quantum world doesn't just exist around us, it operates through us. We are the universe becoming conscious of itself, capable of collapsing infinite possibilities into experienced realities through the profound mystery of quantum observation. In understanding wave-particle duality, we've discovered that consciousness and cosmos dance together in the eternal creation of everything we call real. That's the true answer to our question. Reality doesn't just change when we're not looking, it exists in a state of infinite possibility until consciousness looks and forces it to become something definite. We're not separate from the reality we study. We're the reality studying itself, one quantum measurement at a time.